you remember, in the beginning of this chapter, we said that we have two generators for producing random numbers. The first one was uniform probability density function. We talked about the probability density function, and one of the functions that generate random numbers is uniform one. As you see here, we define the PDF probability density function of uniform type like that. We suppose that our curve and function is defined using this formula. We say that if our x is between A and B, the probability density function of x is 1 divided by B minus A, otherwise is equal to 0. It means that if our event include inside of this duration and interval between A and B, the probability of this event will be 1 divided by B minus A. And if our A is equal to 0 and B is equal to 1, the probability of each event that include this interval will be 1, otherwise will be 0. As you see here, the probability here is uniformly changed. Uniformly changed. Now, if the event x, random variable x, occurred at this interval x1 and x2, that x1 is greater than A and x2 is less than B. So how can I find the probability density function of event x that is between x1 and x2? I can say that we learned that the area under this curve give me the probability of that event. So it means that if I can calculate the area of this triangle, this area of this rectangle, I can find the probability of this event. So how can I calculate this area? I can say that the height of this rectangle, which is equal to 1 divided by B minus A, times the width of this rectangle, which is equal to x2 minus xy. It means that x2 minus xy divided by B minus A is my px of x. Px of x. Okay, the second form of random variable generator is Gaussian probability density function. As you see here, the form of this curve is bell-shaped. This curve is called bell-shaped. Bell-shaped. And the random variables changed inside of this curve. So we learned about the mean and variance and standard deviation. So if you look at here, the Gaussian function or the probability density in Gaussian function is changed like using this formula. As you see here, we have a standard deviation. The standard deviation represents the spread of data about mean value of random variable. And also, this term represents the amplitude of this curve. 1 divided by square root 2 times pi times a standard deviation, sigma of x, multiplying by the exponential to the power of minus x, minus mu of x, mean value of this function, to the power of 2, divided by 2 times variance of the random variable. As you see here, the first step is sigma of x, the second step is 2 sigma of x, and third sigma of x. This curve is going to the infinity and minus infinity. Infinity and minus infinity. It means that our random variable can be selected between minus infinity up to the plus infinity. But 90% of data are between minus 3 sigma x up to the 3 sigma x. 90% of random variables change between this duration, minus 3 sigma x up to the 3 sigma x. For example, as you see here, if the mean value is 0, and for example, if a standard deviation is equal to 2, it means that our random variable changes between minus 6 up to the 6, 95%. Okay, if I suppose that mean value of random variable g, I call the random variable here g, is equal to 0, and the variance of these variables is equal to 1, so the standard deviation will be equal to 1. In this case, I can define the standard Gaussian PDF like that. I can say that 1 divided by square root of 2 pi times e to the power of minus x squared divided by 2. This formula is this one. I substituted 0 instead of mu and 1 instead of a standard deviation and okay. The probability density function described random variables that produces random numbers that can have any value within the interval 0 up to the 1 in the case of uniform density function, and minus infinity up to the infinity in the form of Gaussian function. Now, if random variables produces values that are members of a set of discrete values, we need to change the description and call it probability mass function. Probability mass function, because the member of set of discrete values are in the form of discrete, not continuous. Because our set of random variables are discrete, so instead of probability density function, we will have probability mass function. Probability mass function. So the probability mass function of variable x at xi point, for example at x1, is equal to this value. The x2 is equal to this value, the probability. x3 is equal to this value up to the end of this sequence. This sequence changed from 1 up to the n if I have n sequence of random variables, f sequence of random numbers. So now this random variable, according in other words, over the random variable, we can operate some arithmetic operations. Now I want to show you the random number arithmetic. We learned that a processor manipulates the detected data like that. This is the random variable, and SI is our data. We said that the noise is added to the data. Because this noise is random, we represent our detected data with noise, or our noisy data, with a random variable xi. Okay, so this Si is our signal sequence. This data is not random, is detected data. So the Ni random noise sequence is added to our detected data. So the output of processor can be calculated using this formula. The summation of detected data times random variables. Detected data times random variables. So if I substitute Si plus Ni instead of Xi, I can find that the random section will be equal to Si square, summation of Si square. It means that each sequence is added with together plus SI. SI is my detected data, NI is my noise. The output of processor can be found using this formula. So our goal here, our purpose here is determining the mean of output, variance of output, and probability density function PV of x. PV of x. What we want to learn is that we want to determine the mean of V, variance, and probability density function. Okay, so to reach this aim, this processor operation involves three arithmetic manipulations. The first one is adding a non-random constant value, adding non-random constant value to the random variable, multiplying a random variable by a non-random constant, and the third one is adding independent random variables. Let's investigate these three arithmetic manipulations. What can I do? I want to add a constant value to the random variable. This is the constant value. So Gi is a Gaussian random variable. Y1 is again the Gaussian random variable with adding a constant. So we suppose that our Gi is a standard Gaussian function. The mean of G is equal to 0. So what about the mean of Y1? A plus of 0 is equal to A. It means that the mean of Y1 has been shifted from 0 to A. What about the variance? Because only we have shift completely at the all of the form of the bell-shaped curve, the variance will not change. The variance will not change. It means that the variance of Y1 is equal to the variance of G. Okay, so the PDF of Y1 at point X will be the PDF of G at X minus A. It means that instead of X, if I substitute X minus A, I can find the PDF of new random variable. As you see here, this is PG with the mean value of 0. If I add an A value, for example, I suppose that A is equal to 3. What happened? My bell-shaped curve, my Gaussian function will shift to the right with the A value. it means that my average value of functions changed from 0 to the A. As you see here, my data random variables changed from this one to this one. If I add A and my A have to be positive, all of the random variables upward to the positive section of my coordinates. But as you see here, the variance and standard deviation is not changed, are constant. Okay, now if I multiply a random variable by constant, now I multiply the G1. What happened in this case? In this case, because I said that mean value of G is equal to 0, if I multiply by a constant value with a 0, it means that my mean value will be 0. In this case, my mean value will not change, but I will have change in the form of probability density function, in the form of bell-shaped curve. If my A is greater than 1, the PDF of Y2 is stretched, and if A is less than 1, the PDF of Y2 is contracted. Look at here. Look at here. The mean value will not change if I multiply by 2, because 2 is greater than 1, my PDF, my bell-shaped curve is stretched. So what happened in this case? In this case, my variance will change from sigma squared to the A squared times sigma squared. And my probability density function is changed like that. And also I will have change in the variance of probability density function. Again, you can see that if GI is changed like that, when I multiply GG with A, for example, if A is 0.5, you can see that how our amplitudes of data or random variables change. The third one is adding independent random variables with together. If I suppose that the random variable x1 and x2 are independent with together, okay, and the mean value of x1 and x2 is equal to 0, and the variance are sigma to the power of 2. So the third random variable can be represented like that, x1 plus x2. It means that I have to add the mean values with together, because the mean values are 0. The mean value of y3 is also 0. And the variance of x1 will be added with the variance of x2 to calculate the variance of the y3. As you see here, I will have change in the amplitude of y3 according to the amplitude and value of x1 and x2, and my probability density function changes like that. If I substituted the actually standard deviation and variance of y3 into the Gaussian function, I can find this y3p. As you see here, again, my mean value does not change. Only I will have change in the standard deviation and also amplitude, because this term of function represent the amplitude. Okay, what did we learn here? We learned that how can I model a noise and produce random variable.